These functions, the spherical harmonics, are also shown using another type of symbols. S functions. For L equals 1, there are 3 m values. 1, minus 1, 0, minus 1. All of them are indicated by a P symbol. And then the subscript P1, P0, and P minus 1. These are the symbols for the 3 P functions, which means these functions, spherical harmonics, L equals 1 and M equals 1, 0, and minus 1. For L equals 2, there are M values are 2, 1, 0, minus 1, minus 2. These are indicated by all of them with the symbol D, but the M values are attached as subscripts. So this is D2, D1, D0, D minus 1, and D minus 2. There are 5 D functions. So these symbols that you see here indicate the YLM functions. And these orbitals are, in general, complex orbitals. Only P0 and D0 are real functions. The remaining functions are, S functions, of course, are real, because M is 0 over there also. But P1, P minus 1, D2, D1, D minus 1, D minus 2 are complex valued functions. In preparing graphs related to the angular functions, it is preferable to use real valued functions for all. This can be done, and we will discuss how it is done. So a proper title is Using Real Functions instead of these are complex valued functions. Now, for a given value of L, there are 2 times L plus 1 M values. I will indicate the possibilities in the following way. For a given value of L, there is always a 0. There is 1 and minus 1. There is 2 and minus 2. And the largest value is L, and there is also minus L. From this line, you may also see how many different M values there are. M. If you start from here, how many parentheses do you count? L parentheses, because starting value is 1, last value is L. There are L such parentheses. Each parentheses contain 2 numbers, 2 times L. plus this 0. 2L plus 1. Different m values. This is already real. The spherical harmonics, these functions, are complex values for all the rest of them. What makes it complex? Here we have this factor makes it complex. Because the first factor, which depends on theta, is a real function. Now, if we take that factor, the right side is the definition of how to calculate e to the a complex number. M is a real number, phi is a real number. You calculate cosine m times phi, and also you calculate sine m times phi. The first factor is the real part, and sine is the imaginary part of this complex number. Now, we may also write for the negative of the same m value, the only difference is a sign here. All right. Now, let us count how many functions, how many different functions there are here. One function is this, e to the I times m phi. Another function is this one. These are different functions, aren't they? That makes 2. Cosine is a third function, and sine is a fourth function. So we can write there are 4 functions. 2 of them are complex valued, and the other 2 are real valued functions. Cosines and sines are real valued. Now, are these 4 functions all independent? In algebra, if I say there is x, y, z, how many variables do you count here? 3 variables. If I say and then I ask you, how many independent variables are there with this data? You count the number of symbols. How many? 3. 3 different symbols. But there is one relationship between them. So what do you conclude about the true number of independent variables? 3 minus 1, isn't it? Only 2 independent variables here. Independent variable means you take one of them, x say, you may assign any number to it. Then take the second variable, say y. You may also assign any number to y. But when you come to z, you have to think about this relationship. So you cannot just put any value to z. That's what it means, independent variables. Same reasoning applies to functions. You count how many different functions there are. And then you count how many relations are there. So we have 4 functions. But how many relations which relate those four functions? Two relations. Four minus 2 is 2. This means that among these four functions, only two of them are independent functions. Because if you select any two out of the four, and then the remaining functions, they are also two in number, are going to be obtained from these relations. Now, which two functions should be selected? It is arbitrary. You may select any two. Using spherical harmonics, y functions, implies that we have selected these two functions, the complex functions. All right? But we could also select cosine and sine. If we select cosine and sine, then our functions are going to be real valued. We take cosine, this function. Let us also make sure it is normalized, and the normalization factor is 1 over square root of pi. This I will call capital C m. C reminds me of cosine. Similarly, I will take the sine function, and the normalization factor is 1 over square root of pi. I will call it S m. These are my phi functions. For m equals 1, 2, 3, up to L. The normalization of these functions is like this. What is the full range for phi? 0 to pi or 2 pi? Remember, we have two angles. One is theta, the other is phi. Phi, this symbol, phi, goes from 0 to 2 pi. It's complete round trip. 0 to 2 pi, all right? Full range. So the square of it times d phi, full range, 0 to 2 pi. If you select this 1 over square root of pi as the factor which multiplies, then the value of this integral is going to be 1 for all n, from 1 to L. Same thing, similarly for the cosine factor. Instead of S, the sine function here, you substitute cosine. The value of this integral is 1. Okay, now, instead of taking these factors, now we take t times L multiply with the cosine part, and now I don't need this absolute value, and for m equals 1 to up to L. So if we now count how many functions we have L functions, which is this factor times cosine part, another L function, which is this factor, that makes how many as a total? 2 times L. These are all real functions. Plus m equals 0 function, which is y as 0. This is already real. Therefore, instead of using 2 times L plus 1 complex functions of the spherical harmonics type, we are allowed to use those two. There are 2 times L such functions, plus this one, it makes 2 times L plus 1. All of these functions are real valued functions, and they are equivalent to using original spherical harmonics. Now, once again, such notation, the notation here is using complex spherical harmonics. When we use these, now that these are real functions, where shall I write? Let us erase this part. When L is 1, M is 1. In this notation, we are using just the positive values for M. The first factor is Px, Py. Px is T1, 1, L is 1, times cosine 1. Py is again T1, 1, times sine 1. And there is a Pz, which is same as y1, 0. These are the notations for those functions for L equals 1. Px function, Py function, and Pz function. Explicitly, I can write the Px function. This is a normalization factor, a constant, times sine theta times cosine phi. This cosine phi comes from here. M is equal to 1. And the first term, sine theta, is this factor, T1, 1. Py is a normalization constant times sine theta times sine phi. And Pz is a normalization constant times cosine theta. These are the three real functions. Here n is the normalization constant square root of 3 over 4 pi. For L equals 2, we are going to have 5 functions. The complex functions are P2, P1, P0, P minus 1, P minus 2, sorry, D. D2, D1, D0, D minus 1, D minus 2. These are 5 complex D functions of angles. The corresponding real functions are indicated by the following symbol. dz square. This is same as y2, 0. The remaining 4 real functions are obtained using from these. Their symbols are d sub xz, d sub yz, d sub xy, and the last one is indicated by dx square minus y square. dxz, dyz, dxy, and dx square minus y square. I want you to understand clearly why these subscripts are used in these functions. Please remember the relationship between Cartesian type variables and spherical polar variables. What are the relationships? X, Y, Z, Cartesian, r theta phi, spherical polar variables. Relations are x equals r times sine theta cosine phi, y is r times sine theta sine phi, and z is r times cosine theta. These are the relationships between Cartesian type xyz variables and polar variables, r theta phi. Okay, now what do you see here? X. What is the actual expression? Sine theta times cosine phi. Here. Because of this relation, the x subscript to p is used. Same thing is for py. What is py? Sine theta times sine phi. That you see here. And what about pz? Cosine theta. Here. You just ignore the r factor. Just look at the angles here, and it is the same expression. Now, this type of, this is the reason why d orbitals are also indexed, except for this one. But say dxz. This you should read as x times z. All right? Now, in the x part is this. Sine theta times cosine phi. Z is cosine theta. And of course, there is going to be some overall multiplier to normalize it. But this is the explicit expression for d sub xy, xz. What about d yz? This y times z. Y sine theta, sine phi, and z is cosine theta. So a normalization constant. Similarly for d sub x times y, then you will take this times that to write the actual expression. Let us look at x squared minus y squared. X squared sine square theta cosine square phi, square of this term, minus square of this part. All right. Now, the expression for dz square is not exactly like this, its definition, but of course, dz square doesn't contain phi variable. It contains only theta. Dz square a normalization constant times 3 times cosine square theta minus 1. But nevertheless, you see z is this part, cosine theta. There is a square, dz square. You see cosine square over there. But the fact that it is multiplied with 3. And there is also an additive constant, minus 1. All right. We are going to use the real functions of the angles to discuss the probability density as a function of angle orientation. This is the state function, which is radial function times the angular function. For y, we may either use the actual spherical harmonics, which are complex valued, but instead of them, we may use such real functions. It doesn't matter. We are going to use the real functions in our graphs. Psi square times d tau. This is probability, isn't it? Probability of finding the electron inside a tiny volume, which is d tau. So psi square itself is probability density. We may interpret the probability density as charge density. Why? Because the charge on the electron is minus 1. That's the total charge of the electron, on the electron, minus 1. So, because we are taking elementary charge as our unit of charge, psi square can be interpreted as the electronic charge density. Charge density. Or explicitly, r square times y square. Now, this part describes the dependence of the charge density on distance from the nucleus. Okay, that one we discussed. The radial probability distribution function is directly the charge density distribution function with respect to R. How the charge density changes with distance from nucleus. That is related with this factor and multiplied with small r squared. Now we are going to look at this part. That part contains the angles. There are two angles, theta and phi. So now we are going to discuss the angular dependence of the charge density from the y functions. For this purpose, we use polar graphs. Polar graph. Let us say phi is the variable. And there is a function which depends on phi. Then we draw two Cartesian directions and then measure, say there is a point, measure this angle, phi, calculate value of the function at that phi, and then place this mark from the origin. This is origin, this is phi. This distance is value of the function you are plotting. And you put a mark here for that phi. This, and then now you pick another phi value, calculate f value, say that one. Then this is another phi angle. This distance is the value of this function, same function, but at the new phi value. You put a mark there, and you continue like this, then connect the tips here. This is how polar graph is done. Now, for an s orbital, for s type angular function, S functions, the angular parts, do not contain any angles. It's just a constant. This is just 1 over square root of 4 pi. And this factor comes from the normalization. So, but for the qualitative graphs, it doesn't matter. So, if you plot graph of S function at any angle, you obtain a circle. So, say, this is the value of the S function. It is the same for all phi angles. So, when you plot the polar graph, you just obtain what? A circle. Probability or charge density is the square of it. So, if you take the square of these points on the circle, you obtain another circle. So, for the s orbital, charge density is like this, but how do you interpret this? In an s orbital, we have orientation or different orientations. They are specified by the angles, theta and phi. According to this picture, at all angles, the charge density is the same. All right? That's characteristic of s orbitals. Charge density is, you may say, spherically symmetric. In other words, it doesn't depend on direction. At any angle, it is the same. It just depends on the radial distance, but radial distance is contained in the first factor. For p orbitals, here is the actual function. This is we are going to use for f. But I'm going to plot the square of it to indicate the dependence of charge density on the angle. Now, there are two angles here. So what I do is I select one of them, say theta angle. I'm going to select it as 90 degrees. Remember, theta is measured from the z-axis. When I select theta as 90 degrees, then it means I'm on the xy plane. So, this is x, this is y. The function I'm going to plot is sine 90 is 1. Only this cosine here. Take the square of it. Cosine square phi. This is the charge density for the px orbital. All right? Now, phi is measured from the x-axis. So, for instance, phi is 0. Value of this function is 1. Then I increase phi. It starts to become smaller than 1. So it goes like that. But remember, range of phi is from 0 to 2 pi. At pi over 2, what is the value of this function? 0. And then it goes on like that. The two sides should be symmetrical. Should be same as that one. This is like two American football ball attached to each other. So these are not circles. They are a circle elongated from the two sides. This picture shows that charge density in a px orbital, which is the polar graph of this function, square of it, is concentrated along x direction. You see that along the y direction, along points on the y-axis, this function has 0 value. It means charge density is 0 along the y-axis. Now, in the actual graphs, or in the graphs that you see in other textbooks, the charge density or probability density is sketched. After that, the sign of the function, orbital, cosine phi. This is square. This is the original px orbital. Cosine phi has a positive value for phi 0 to pi over 2, and after pi over 2, it takes negative values. Also for pi in the third quadrant. So we indicate them by some color or drawing it like that. In other words, one side is made different from the other side. This means that there is a sign change between the two parts. But sign change in which function? In the cosine function. Because there can be no sign change in square. Square is always positive. It cannot change from from plus to minus. The sign change is indicated like this. Such sign changes, showing them is useful in qualitative applications of such orbitals in, for example, organic chemistry. Organic chemistry qualitatively uses such orbitals in discussing many things, bond strengths, reactivities, and so on. And the sign changes in the orbitals is important in those discussions. Let us continue with others. Py orbital is similarly drawn by putting theta equals 90 degrees, so on the xy plane. This is for Py square. This is proportional to sine square phi with on the xy plane. Sorry, this part. It's exactly this picture, rotated 90 by 90 degrees. So the picture is showing that the charge density in a Py orbital is concentrated along y direction. Similarly for the z orbital, Pz. To draw the Pz, you should remember that theta is measured from which axis? XY, look, theta phi. These, you have to remember from which axis they are measured. Phi is measured from x-axis, theta is measured from z-axis. Any point on the z-axis has theta equals 0. Starting value for theta is 0. So take this as z-axis, because we are measuring theta from z-axis, and this one, y-axis, x-axis is perpendicular. We are drawing it on the yz plane. What are we drawing? Square of this function. Cosine square theta. All right. The polar graph looks exactly like these. And as you expect, charge density in a Pz orbital is concentrated along z direction. Very quickly, let us look at these d orbitals. this is for dx square minus y square. The polar graph. You may easily understand the sign changes. The sign in this part is opposite of the sign over there. If it is positive here in the open part, sign is negative on this side. This is the charge density drawn for it. You see that here L is 1. Let us start from here. Now, what is this plane here? This direction is z. This is yz plane, isn't it? This charge density is 0 at all points on the yz plane. Similarly here, this plane. What is this plane? X and z this way. XZ plane. Py orbital is 0 at all points on the xz plane. So far, there is just one plane for the px orbital 0 to be 0, one plane for the py, and also one plane for the pz orbital. What is the plane? This plane. This direction is which direction? Z is vertical. Y is horizontal. Perpendicular to the blackboard is which direction? What is the remaining letter? X. So, X, Y plane. There is a plane. All right? This is how is it described? By telling the names of two axes. This is Z, this is Y. So at every point on this plane, this function is 0. Such planes are called nodal planes. One nodal plane. In other words, it's a plane on which everywhere on the plane the function is 0. That's what's a nodal plane. P orbitals have just one nodal plane. Look at this one. There is a plane which is at 45-degree angle from the x-axis. Imagine such a plane. Everywhere on this plane, this function has 0 value. Therefore, it is a nodal plane. There is another nodal plane. And there is no other nodal plane. So if you count how many nodal planes there are, what is the answer? There are 2 nodal planes for the D functions. Now, the number of nodal planes is directly related to the L value. All right? Look at over there, P. What is L? 1. How many nodal planes are there? 1. Here, I have shown one of the D orbitals or the charge density for the d orbitals, but number of nodal planes is the same in dx square minus y square, also square of it, because when you take the square, can you change the zero plane? If I say a function has 5 nodal planes, information given to you, then I say, how many nodal planes are there in f square? Same number, isn't it? It could be f cubed, f to the fourth, because as long as f itself has that many zero planes, every power of it will also have the same number of nodal planes. Our time's up. But there are 5 d orbitals. All of them have 2 nodal planes. For example, this is, let us make it last. This is dx times y. And here is one nodal plane, which is what? XZ. Sorry, YZ. YZ plane. Yes. And also another one. What is this? XZ plane. There are just 2 nodal planes here also. Okay. The other polar graphs of the remaining 3 are available in the notes. All of them have 2 nodal planes. In general, number of nodal planes is equal to L. So s orbitals have L equals 0. That means they have no nodal plane.